I keep a close watch on this heart of mine. I keep my eyes wide open all the time. I keep the ends out for the time.
In this video, we'll begin our discussion of algebraic extensions, which is the subject of section 13.2 of Dummett and Foote. And this is one of those places where Dummett and Foote make a statement at the beginning of the section that's supposed to hold throughout the section and they don't continually remind you of it as they use it. And that is, f is always going to be a field and k is always going to be an extension of f. So for the rest of this section, which will take us through this lecture, the next one, and I think even part of the one after that, f is always going to be a field and k will be an extension of f. All right, so what does it mean first for an element alpha in k in this extension of f to be algebraic over f? That means that alpha is a root of some non-zero polynomial in f bracket x. And in the case that alpha is not algebraic over f, then what does that mean? That means that it's not the root of any non-zero polynomial in f bracket x. Then we say that it is transcendental over f. So these elements of this field extension k can either be algebraic, or if they're not algebraic, they're called transcendental. So what does it mean for an extension to be algebraic? That means every element of that extension is algebraic over f. So the extension k over f is algebraic if every element of k is algebraic over f. And the thing that we're aiming at for the rest of this lecture is corollary 13 in section 13.2, which says that if k over f is a finite extension, then it is an algebraic extension. So finite extensions are algebraic. All right, so one first thing to note is you have some element alpha in some extension of f. If it's algebraic over f, then it's also algebraic over any extension of f. So how does that work? Well, if alpha is algebraic over f, that means it's a root of some polynomial in f bracket x, some polynomial with coefficients in f. So if L is some extension of f, then f of x is also a polynomial in L bracket x because f is a subfield of L. So we have this one polynomial in f bracket x where alpha is a root. We get another polynomial in L bracket x, the same one, but now you think of the coefficients as elements in this bigger field, and alpha is still a root of this polynomial. So this alpha is also algebraic over L because it is the root of a non-zero polynomial with coefficients in L. Okay, so what I want to do now is talk about the minimal polynomial of this element alpha of this extension of f. And one of the key things that we'll prove in this lecture is proposition 9 in section 13.2, which says, let's suppose that alpha is algebraic over f. Then there is a unique monic irreducible polynomial m alpha comma f of x. This is a polynomial in f bracket x that has alpha as a root. Okay, so for notation, alpha is this element that this polynomial has as a root, and f, we want to emphasize that this polynomial is in f bracket x because you can talk about the corresponding polynomial for the same element alpha, not with respect to this field f, but with respect to some other field, say like with respect to L, and they may not be the same, and I'll talk more about that soon. So, okay, there's this unique monic irreducible polynomial that has alpha as a root. What happens if we look at the collection of all the polynomials in f bracket x that have alpha as a root? Well, any polynomial f of x in f bracket x has alpha as a root if and only if it's divisible by this special polynomial, which is called the minimal polynomial of alpha over f. Okay, so I'll pause and erase, and I'll give a careful definition of the minimal polynomial And I'll state a corollary of this proposition that follows directly from it. Actually, two things that follow directly from it, and then we'll prove this proposition. An immediate corollary of this proposition 9 is corollary 10, that if L over F is an extension of fields and alpha is algebraic over F, we already know that because L is an extension of F, it's automatically algebraic over L. So we can define this minimal polynomial of alpha with respect to F, the minimal polynomial for alpha over F, and also the corresponding polynomial over L. And we see that M alpha Lx divides M alpha Fx in L bracket x. And the proof is one sentence. What do we know? Well, this M alpha F of x is some polynomial in L bracket x that has alpha as a root, right? L is an extension of F. So you take this polynomial that's in F bracket x. It also gives a polynomial in L bracket x. But we know that there's this unique monic irreducible polynomial M alpha L of x. And any polynomial in L bracket x that has alpha as a root is divisible by this one special polynomial here. So that's the whole proof. Okay, proposition 11 is also an immediate corollary of this proposition 9. It says, let alpha be algebraic over F, and F adjoint alpha, this is the notation for this field, generated by alpha over F. Then F adjoint alpha is isomorphic to the quotient of F bracket x by the ideal generated by this M alpha F of x. And so the degree of this field extension is the same as the degree of this field extension, which is the degree of this polynomial. And what is the proof here? The proof follows immediately from this theorem 6 from last time, which relates the field that you get, the field generated by alpha over F, where alpha is a root of an irreducible polynomial contained in some extension of F. What's that polynomial that alpha is the root of? It's the root of this irreducible polynomial M alpha F of x. Okay, so I'm not going to keep saying M alpha F of x. This gets a name. This polynomial is called the minimal polynomial for alpha over F. And this degree of this minimal polynomial gets a name. This is called the degree of alpha. So when we say the degree of alpha, we're dropping the F in that terminology, but this really is defined with respect to F, because as you change from F to L, this minimal polynomial for alpha over F and the minimal polynomial for alpha over L might not be the same. So, okay, you should be aware of this. Oh yeah, so I'll say that the degree of this field extension is the same of the degree of the minimal polynomial, which by definition is the degree of alpha. Okay, right, so just as a quick recap now that I've said this out loud, what are we saying? If L is an extension of F and alpha is algebraic over F, it's also algebraic over L. And we see that the minimal polynomial for alpha over L divides the minimal polynomial for alpha over F. So if you just think about what that means in terms of degrees, for the bigger extension, the bigger field, the minimal polynomial can have smaller degree. So it certainly can't have larger degree than the one for the smaller field. Okay, so if we prove proposition 9, then we'll immediately prove this corollary and this other proposition. So I'm going to pause and erase, and then we'll do the proof of proposition 9. Let's prove proposition 9. We want to show that there's a unique monic irreducible polynomial that has alpha as a root. And the idea is to take a polynomial of minimal degree in F bracket x having alpha as a root. So that's going to be g of x. So there's no guarantee that the polynomial we took is monic. So we can scale our polynomial by a unit in F bracket x. So we can scale by an element of F star. without changing the roots at all. So that means that there is some monic polynomial of this minimal degree having alpha as a root. So we're going to show that that polynomial is irreducible, and it's unique, that it's our unique monic irreducible polynomial having alpha as a root. So let's call that monic one g of x. All right, so first let's show that g of x is irreducible using this assumption that it has minimal degree among all polynomials that have alpha as a root. So let's suppose it wasn't irreducible, so it's reducible. That means it factors as a of x times b of x, where a of x and b of x are in f bracket x, and they both have degree smaller than the degree of g. So now we have this equality of polynomials. If we evaluate both of these polynomials at alpha, we have to get the same thing because they're the same polynomial. So g of alpha, which we know is 0, is a of alpha times b of alpha. So how could a of alpha times b of alpha be 0? These are two elements in f that multiply to 0, and f is a field. So one or the other of these has to be 0. So that means that alpha is either a root of a or it's a root of b, but they both have degree smaller than the degree of g. So this contradicts the assumption that g of x was a polynomial of minimal degree having alpha as a root. Okay, so that shows that g of x is irreducible. So the only thing we have left to do is we want to show that if f of x is any polynomial in f bracket x that has alpha as a root, then g of x divides f of x. Once we do that, we'll be done. Why? Because we know that g of x is a monic polynomial of minimal degree having alpha as a root, and we know that it's irreducible. But we have to show that it's unique. So once we have this statement, if you had some other monic polynomial of minimal degree of that same minimal degree having alpha as a root, then g would divide f, and f would divide g. So g would be equal to f. So this shows that g of x is the unique monic polynomial of minimal degree having alpha as a root, and this statement in the box is the second statement. So all we have to do is prove this last statement in a box. So I'm going to pause and erase and finish the details of the proof. Let's finish this last piece of the proof. The idea is we have f of x is some polynomial that has alpha as a root. We know that g of x is this monic polynomial of minimal degree having alpha as a root. Let's apply the division algorithm in f bracket x. And we see that there are polynomials q of x and r of x in f bracket x such that f of x equals q times g plus r, where either r equals 0 or the degree of r is less than the degree of g. All right, what are we going to do with this expression for f? Well, this is some equality of polynomials. We evaluate both sides at alpha. We have to get equal things. So we get f of alpha on the left, but we know that's 0 because alpha is a root of f. And on the right, we get q of alpha times g of alpha plus r of alpha. But g of alpha is 0. So we just get r of alpha. So that has to be 0. And that means that this polynomial r of x must be 0. Because if it's not 0, then it's some non-zero polynomial with degree less than the degree of x, and alpha is a root of r. But by this assumption that g of x had minimal degree among all polynomials in f bracket x having alpha as a root, r has to be equal to 0. And once we know r is 0, now we see that g of x divides f of x. And that completes the proof. So I'm going to erase, and then I'll end this video with a couple of quick examples of minimal polynomials. I want to end this video with a few examples of minimal polynomials. Square root of 2, that's an element of R, which is an extension of Q. And I'm going to use the symbol square root of 2 to denote the positive square root of 2. So this is 1.414, and so on. This is algebraic over Q. What's the minimal polynomial? Well, that's a unique monic polynomial in Q bracket X that is irreducible and has square root of 2 as a root. X squared minus 2 is a monic irreducible polynomial having square root of 2 as a root. So it is the minimal polynomial. And that means that Q adjoin the square root of 2 the field generated by square root of 2 over Q has degree 2, the degree of this minimal polynomial. Same idea exactly. Let's do the cube root of 2, the real positive cube root of 2. So it's also algebraic over Q. It's a root of this monic irreducible polynomial x cubed minus 2. So the degree of the field generated by cube root of 2 over Q is 3. More generally, you could do this with not just square root, cube root, but the nth root. The positive real nth root of 2 is algebraic over Q. It's the root of the monic, or it's a root of the monic irreducible polynomial x to the n minus 2. How do we know that that's actually irreducible in q bracket x? Well, it's Eisenstein at p equals 2 tells you that this is irreducible. So that means that the degree of the field generated by the nth root of 2 over q is n, is the degree of this polynomial. Okay, so the last example, I just want to make a point that it really does matter what field you look at the minimal polynomial over. So the nth root of 2 is also algebraic over the real numbers. It's in the real numbers. So what is the minimal polynomial of this algebraic element, nth root of 2 over r, the minimal polynomial for nth root of 2 over r? Well, it's just the linear polynomial x minus the nth root of 2. So this is a monic irreducible polynomial in r bracket x. It's irreducible because it's linear, and it has the nth root of 2 as a root. So this is kind of an extreme example, but if you have, this is something that we'll see throughout the rest of the course, that as you change the field that you're looking at, here it's Q, here it's R, maybe you could pick something in between, the minimal polynomial will change. So it's important to really think about what is the field that you're thinking about your minimal polynomial being over.